Right, I'm actually not really here to talk about the Polestar Zero project itself, but it does give some context to the project which we did do with GRM. Also, I haven't prepared anything to tell you about Polestar at all. When I first joined the company about 3 years ago, I spent quite a lot of time having to explain who Polestar are, and it's becoming less of a problem nowadays. But for those of you who don't know, we are an EV company. We make electric vehicles only. We started in 2017, floated last year. We're a separate company to Volvo, although we did spring from the loins of Volvo and ultimately Geely Group. And when I joined, there were about 100 people, I think, and now in the Coventry office, it's about 750 odd. So we've expanded pretty quickly here in the UK in a couple of offices, a place at Myra, as well as in Bingley, where I am at the moment. Yes, so let's get going with this. So basically, as I said, the Polestar Zero project is half of my work, along with the rest of the advanced engineering team. And so what that's about, so basically the automotive industry is not really, it's probably the biggest, or one of the biggest emitters of CO2. And we are not really on track to meet the Paris climate agreements in 2050. So we really need to make some pretty major changes to achieve that. So if we look at an EV versus a typical internal combustion car, the EV is better over its lifetime. Ultimately, though, you could probably get about half of the CO2 emissions of a typical ICE vehicle. So what you see there is the XC40, which we use as a platform for the Polestar 2. And that figure there is for the CO2 emissions if we actually had completely renewable energy as a supply. But as you can see, you still have the manufacturing stage, which is the issue which we're trying to sort out with the Polestar Zero project. So what the Polestar Zero project is about is unique in that it's not yet the vehicle program. It will ultimately become a vehicle program to be released in 2030. But the idea is that we want to make a zero emission car without any offsetting, zero carbon, including all the stages of production. So that's not just the manufacturer, it also goes into the materials itself, and then all the way back to extraction of those materials. The use stage, as it's an EV, we can assume we have renewable energies for that. But at the end of life, you also want to look after what happens to the product when it reaches the end of life, where it could be recycled or upcycled. So we're also trying to make that zero GHG as well. And this really summarizes Polestar Zero, just a very brief video. So, the Polestar Zero project is split into three basic phases. So ultimately, this is a normal product development cycle here. For this, you'd assume, as say, a level one would be a part that you could produce now with a known manufacturing process, materials that we understand. But of course, to get a zero CO2 car, there's very little around that can do that. So we realize we have to do more work. So there are materials and there are manufacturing processes that exist out there. They're not necessarily within the car industry, but this is really the period when we would want to capture those and apply them to the product development cycle. And then the level which we are in at the moment, the initial phase, is research. So we've got a number of collaborations with a lot of companies in all the different material sectors, plastics, metals, etc. We have about 25 collaborators at the moment who've joined the Polestar Zero project, and we're talking to many more. And we are researching all the way upstream to chemical level the sources of some of these materials. And there you can see the timelines I explained. So, as I say, we're building these collaborations now. And I guess that's going well in many areas, not so well in others. So we're still talking to various companies. We have universities involved to really research at some very basic level the chemicals that you need to build these materials. So, sorry, I just fumbling my bit of paper here. Okay, so that's really the background to the Polestar Zero project itself. But we were looking at this in the office, and obviously we're in the middle of producing vehicles at the moment. So the Polestar 2 is out in the market. We've already announced the Polestar 3 and the 4, and the Polestar 5 is the vehicle that's being designed in the UK with a new platform. And we wanted to really look at how that's ultimate goal of zero carbon material in our cars can actually be integrated to a normal program. So basically the product development timelines over the years have been compressed and compacted, and all the supply chains have been put in place, so everything works as quickly as possible. And we've always worked for many years now towards the goal of making our products in as cheap as possible and in as an efficient way as possible. But now we're actually having to consider what the emissions or the CO2 output of making these materials are. It changes the direction of what we have to do by a huge amount. So it's really like turning an oil tank around, if you excuse the pun. So basically, what we decided to do, this is the Polestar 5, which we have released as a concept. You may have seen it driving up the Goodwood Hill a few years ago. We took a typical interior component from that, and the task was to design that component or look at the design of it and how we can make it a step change in CO2e. So by using an example part and just the single part, keep doing the life cycle analysis for a different structure or different material, and having a back-to-back comparison, we could really understand where the hotspots were, what we had to concentrate on within a normal vehicle program timeline. So I set the tasks for doing this. I took the original assembly, which we thought was a nice simple assembly to start with. It's not it wasn't the most high performing part of the interior. We chose it as a fairly simple part that we could do a very detailed analysis on that you wouldn't have time to do in a normal program. So, out of interest, how many of you understand life cycle analysis? Are you aware of the life cycle analysis? Hands up. There's a few. Oh, very good. Okay. So those of you who don't, life cycle analysis is a way of measuring the CO2e for a product, and the way it works is you basically get you get your material and how much material you will use, and you get a process flow for how you make your product. You map the process flow in a life cycle analysis software, and then you apply the quantity of material that you would need, and after a bit of jiggery-pokery by the experts in the analysis software, you get an answer back for what the CO2e impacts of that product would be. So we started out with this component, mapped it out, and the first surprise was it's a massive amount of data. In terms of number of parts, probably, well, I don't know, maybe there's 20 components in there, but then you've got about a supply chain of maybe 5 different suppliers in different locations. And then you could take maybe a fixing, for example, a small steel screw, and you go all the way upstream with that to material extraction. The software gives you a list, 200 items long probably, of all the influencing factors that give you the CO2 impact of that component. And when you map that on what you think is a simple component, it's a list, and it would be a PowerPoint that would stretch out through the roof of this building. Hence, I haven't got that in there for you. So we mapped that for the original component, and then we wanted to compare, okay, what happens if you swap in some different materials? So we tried the usual stuff, recycled materials, biomaterials, but using the same structure. But then I wanted to take that further, so taking a step back, we looked at the functional requirements of what that does. It has 3 or 4 basic functions, and just from the function analysis, we then reconsidered, okay, let's just forget how it's structured at the moment, which is not incorrect. It's a very standard automotive component where you use a lot of some carryover componentry, you carry over some sort of design influences, etc. But we took a step back and attacked it in several different ways, because I wanted to try and capture as many different scenarios as possible and map this out. And in doing this, we needed to have some way of measuring. So the product attaches to the body via, I think it's about 7 fixing points. So we kept those fixing points. We have some functional requirements for the component itself. So we have some load factors to input. And so we could get we can measure the performance to make sure that whatever material or structure we used, it would still achieve the same requirements. So it's very key that we had that data as accurate as possible, so we knew how much material we would need, so we could plug this in and get life cycle analysis. Which is where I came to GRM to get that accurate data. And Carl is going to do a bit of explanation of what you guys got up to.
Thank you. Yeah. So this is quite an interesting project really to be involved in, particularly on the GRM side of things. We normally get approached for optimization work either in terms of trying to minimize mass or just trying to generally improve performance overall. So for a project that has more focus on sustainability, we're obviously quite more interested in, particularly as Martin mentioned at the start of the event. We haven't made our own sort of commitment to the climate pledge. We have the unique ability really to sort of do the optimization analysis work using solar power. So that's quite a benefit in itself. It's probably one of the reasons I hope to think that maybe Polestar considered us to do the actual work in the first place. So in terms of the actual analysis approach that we did, or rather my colleagues Frank and Jack did, and I'm just here taking the credit for, we started with a baseline design. So for the purposes of the actual presentation, the baseline material was just a generic plastic. We then took a sort of list of candidate materials to consider, everything from metals. So we've got mild steel, aluminium, magnesium. We've also got alternative polymers in there as well. We've got biocarbonate, polycarbonate, acrylic, and then we've also got the catchily named natural fibre number 1, 2 and 3, which we've sensitised for the purposes of this presentation, but we'll have a quick cursory look at in a second. Once we've sort of got a list of candidate materials, the next step then was to sort of benchmark them really. So in terms of a typical list of low cases we looked to assess, or rather Jack and Frank assessed, it would have been the firmness feel, sort of static, sag, and also sort of MVH low cases as well. That just allows us to whittle down from this list of sort of materials really, which ones we would like to take to the next stage, which is more computationally expensive. So this is optimization stuff, which again we'll take more of a deeper dive in a second. And then finally, once we've arrived at sort of down selected materials, we then go down and pick from these which is the best from a sustainability point of view. Now, I guess some of you probably in the audience were thinking, well, this is quite easy really. It's clearly it's going to be one of the natural fibres. Obviously, as Mike mentioned, when considering life cycle analysis as a whole, it's not just the sustainability of the material itself, but also from cradle to gate you need to consider. So some of the natural fibres, although more sustainable, they can clock up more CO2 miles when you actually consider the source and getting them to the point of manufacture. So that's something to bear in mind. The other thing as well is when we're applying these optimization methods as a whole, the benefit of using it is it allows us to keep it objective, so we can remove the element of human bias from it as well and stop any sort of preconceptions that's just saying, okay, let's go down the route of natural fibre, this is the best way forward. So that's something to bear in mind. So sticking with the optimization route, obviously as analysis, we wanted to sort of really consider which method was best for what particular material. So for example, for metals, some of these sheet form materials lend themselves quite well to topography and sort of swage analysis rather. And some of the materials that could be cast, such as the metals or some of the plastics that are being injection molded, led themselves quite well to topology optimization. Or as some of you may know in the audience, we obviously have our tool RDM, reinforcement derivation method, which is still again a form of topology. Finally, we've got some of the composites then sort of again lend themselves better to more laminate-based optimizations as well. So this is just something we need to consider when we're scoping the materials. And then this next slide sort of goes into a bit more detail then in what these particular materials were and why we've actually arrived them as candidates for this actual zero wing project. So obviously we've got a mild steel, which is commonly used in most automotive applications. We've got a aluminium, the grade of which for this project is used in a lot of the Polestar vehicles itself, so it's quite known to Mike and co. Magnesium, so a high strength material, rather high performance material, which is also fully recyclable. We've got our generic plastic, which is made for the baseline material. We've got our polycarbonate, the polycarbonate alternative. We've got acrylic. We've also got our natural fibres 1 through 3. So to sort of break those down in a bit more detail, try and differentiate them. Natural fibre 1 is a bio-based resin, which has sort of a short natural fibres embedded within it. We've got natural fibre 2 then, which is a press moulded material, which is made from a biodegradable source. But however, it does have the manufacturing process limitation of it has to be derived from constant thickness. So that's something we have to bear in mind on the optimization side. And then natural fibre number 3 then is basically a sustainable material, primarily based from flax and hemp. And it can also be fabricated and treated as a sort of typical conventional laminate really. So it has that going for it too. So once we've got these candidate list of materials, next step then was to try and say, okay, how do we start to weigh up the pros and cons of these in a more sort of quantitative way? So what we did was basically take the baseline design as it stands and then start assessing it for different materials and see what the performance is. So this graph you can see up here is basically just a comparison between the frequency per gram basis. So it's almost like a stiffness per weight ratio indicator in a way. We start on the bottom left over here. We've basically got our baseline design. We've got a line leading all the way along there to sort of make it a bit easier to compare the various materials. See on our y-axis we've got the hertz per gram, so frequency per mass value essentially. You can see steel's not looking too great. The performance isn't that brilliant for what it's worth, so it's not really earning its stuff there. Aluminium, it's doing a bit better compared to the baseline design, so it's got a good factor to bear in mind there. Magnesium is coming out top in this particular graph, but one thing to bear in mind is that it could be too strong for requirements. It could be over-engineered if we do tend to choose this particular material. Apparently the polycarbonate, the biopolycarbonate, they're coming in under the baseline performance, so it's sort of a tick in the negative column, as it were. We've got our acrylic, which is just eking over there, so it's a potential candidate in that respect. And then our natural fibres, although coming in under the baseline design, can actually apply optimization methods to sort of get more benefit from, really. So with these in mind, we basically ended up selecting 3 particular materials to progress to the optimization phase, with these 3 being aluminium, and the acrylic, which is a monomaterial, with monomaterial basically meaning it's a continuous component, which lends itself well to sort of simplified assembly. And the natural fibre number 2, which is, if you can cast your mind back to the previous slide, would basically be a press moulding material, which again has the manufacturing limitation of only being able to be made from a constant thickness. So we took those 3 materials, progressed them to the next stage, and then we said, okay, what optimization methods lend themselves best to these particular ones? So obviously aluminium lends itself quite well to topology, or RDM, we tend to refer to it as GRM. Acrylic, and also natural fibre number 2, they both lend themselves well to gauge or size and optimizations. So we proceeded with that in mind, looking at the aluminium to start with, the topology optimization we've used. We managed to arrive at a value of a 50% mass saving. The sort of greyed out regions you can see on screen are essentially the non-designable portions. So this has allowed us to have like readings for mounting points, the speakers, etc. The structure it's formed is quite organic overall, so there will be some interpretation involved, and we'll lose a bit of this mass saving as a result. But overall, it's not a bad sort of concept, and although it's a skeletal structure, you can obviously have some form of fabric wrapping to go over it to sort of complete the look and aesthetic as a whole. Moving on then, so the other 2 materials, obviously we've got the acrylic and the natural fibre. Just to sort of explain the difference between the top and bottom slides, for those who are familiar in the audience, we've basically got a topometry analysis, which is basically just a form of local size and optimization, which we explored initially. And before then moving on to these global size and optimizations, where we're basically just changing the thickness of the entire component. The reason why we ended up moving away from topometry, local size and optimization, was to global, is for 2 reasons. On the natural fibre stage, the natural fibre number 2 material point of view, is because again we were limited by the manufacturing limitation of it being a constant thickness. And then on the acrylic side of things, you can sort of see we get quite sharp graduations of thickness, which doesn't lend itself particularly well during the manufacture, and isn't ideal really. So this is why we ended up switching to these sort of global size and optimization approach instead. So on screen here, we basically got the interpreted designs for the aluminium after the solid topology optimization, and then the sort of finalized thicknesses for the natural fiber version and also the acrylic version then. So we've got 3 designs essentially to consider. So the next stage then was to sort of say, okay, how do they compare in terms of the actual low cases? So again, just run them through the static strength, the firmness feel, and the sort of sag and MVH cases. There's results on screen here only just for the sag and the MVH, so we don't bore you to death. But essentially the aluminium design possessed the least displacement in terms of sag, whilst the natural fibre possessed the highest natural frequency really, so it's got a tick in its positive column in that sense. So moving on to the next part then was basically to take these results and say, okay, these are what the analytics are saying after we've optimized the results, and we can compare them on a mass basis, and then say, okay, we know what performance is, this is the mass it's offering, and then sort of feed that information back to Polestar and Mike then and say, okay, this is the inputs for your LCA analysis, so life cycle analysis, and then you can sort of take that to the next level and look at it in terms of our overall sustainability offering. So at this point, I'll probably hand back to Mike, who will sort of walk through the results. So, yes.
Thank you. Yeah, so as Carl explained, we had basically 3/4 structures. So we had the original structure where we tried material substitution. Then we had a structure where we separated the structure from the aesthetic. So we just went for example, the aluminium and the magnesium to see, okay, if you have a very high performing material but very little of it, how does that compare to maybe a less well performing material but more of it? Taking magnesium as a case in point, it's not great for CO2 at all. Part of the reason for that, though, is because the process of making it has moved to a process called the fission process, which is very prevalent in China. It's pretty much wiped out any other process because it was very cheap. But you can get magnesium from seawater, and you can recycle it completely, whereas you can't recycle a polymer that easily. So it was interesting for me just to see how it would compare, because you don't need so much of the magnesium. As it turned out, you need so little of the magnesium that you can't actually manufacture it because it's such a spidery looking part. So it wasn't that great. But the point of this program really wasn't a normal project where you wanted one end result. We wanted to understand the whole landscape, where the hotspots were, what you had to concentrate on, what was less important for a product if it was low CO2. So I know people like to have numbers, so the best reduction in CO2 we managed to achieve was of about reduction of about 72%, and that was a step change. And to give you some idea of where that falls, if you use your usual recycled materials, which are getting more and more used these days, or a bio-material, but with the original structure, those results only give you sort of 10-15% improvement. You have to make a step change the structure completely. The monomaterial one was the third of our alternative structures, where you combined a lot of the functions into a single part. That didn't actually come out the best, but it was quite good, mainly because you could drop out some of the electronics. But what it really taught us was that there's no one single answer. That to get the best performing component, it's not a case of, we'll just use this material. You have to consider the whole structure, how it all interfaces, what the integration is, look at the supply chain, how long that chain is, look at the material sources, the extraction, how big that chain is, and ultimately what the end result is when you come to end of life. So as Carl mentioned, for example, there's some amazing composites out there, but one of the problems with composites is once you combine stuff, you've then got to take it apart again to recycle it. So, yes, so basically we had a huge amount of data from this. I guess for me, the most important learning was really to be able to tell our engineering, our normal project engineers, the team, the sort of things that they have to look out for when they're designing the next program. So if we're looking for low CO2 products, there are alternative materials to consider. You look at, for example, if you have to use a polymer, then there might be an alternative polymer that has a shorter chain that is easier to recycle or easier to produce, and it's maybe less high performing, but you still need to get the balance right, because you might be able to increase the quantity of that polymer just a tiny amount and get a far better CO2 result. So I think there's another page here. Yes. Sorry, let me jump back again. Okay, so so in summary, really, the scenario analysis we used was all based on the LCA results. So GRM's input was very key to getting these results, but the point was really getting all these different versions of the same product to achieve the same result, and then measuring how much material that was, and then getting the LCA results from it. And that's what we've managed to learn from. And so we now have a good idea of the hotspots and what we need to achieve to make the next design a better CO2e result. And we continue our work on Polestar Zero as well. And the Polestar Zero ultimate goal is to create a first climate neutral car by 2030. And we hope to become a climate neutral company by 2040. And in the meantime, the information from this study we'll use to increase or improve our sustainability results for our products in the interim. And that really completes the presentation. Thank you very much.